for me? Oh, we're live. All right. So example 10 is going to be kind of like the warm-up, except we're adding a couple of extra spinning things to it. And it's going to make it more fun. All right, let's talk about a bicycle. Everyone in here knows how to ride a bicycle, right? And if not, maybe you've forgotten. I don't think so. Everyone at least here knows how to swim, right? You don't want to be like Clementine. Ooh, yeah. So a bicycle has a pedal sprocket with a 9-inch diameter. It has a wheel sprocket with a 3-inch diameter. And it has a wheel itself, which I'm going to call the tire, with a 29-inch diameter. So this is one of those newfangled 29 bikes. If the bike is being pedaled at 35 revolutions per minute, how fast in miles per hour is the bike traveling? Suspense. Down the road. Okay, cool. So let's go ahead and draw a bicycle-ish, okay? By bicycle-ish, I just mean I'm not really an artist, but I think there's a tire. There's one, snapped to circle. We'll make it kind of big. There it is on the road. And we'll just copy that one, and we'll paste one over here. Okay, so there it is. Those are the two tires, all right? So I'm going to go ahead and label this radius. I'm going to call that the tire. So let's put a little cola in there. The tire has a radius of what? If the diameter was 29, what's half of 29? 14.5. Okay. It has a gear radius on the back, which I'll snap to circle again, make it a little bit smaller, and then we can kind of center it up if you want. There we go. So that's what I'm going to call the wheel sprocket. We'll call that W. And if that's 3 inches all the way across, what's the radius of the back wheel gear? 3 inches across means 1.5 inches radius. Okay, and then we have this guy. Let's use green. There's a pedal sprocket right here in the middle. We'll make that a little bit bigger. There it is. We'll call that the pedal sprocket. And it has a 9-inch diameter, so the radius is 4.5. All right, so we have 3 different radii. The pedal, 4.5, which is attached to the wheel, 1.5, which is on the same axle as the tire, which is 14.5. Okay? So if the pedal is moving at 35 miles per hour, or 35, RPMs, we want to know how fast is the bike moving down the road in miles per hour. All right? So now we got to work backwards from there. First of all, let's go ahead and draw something that's missing. Handlebars. No, those aren't important. What's important is what's connecting the pedal gear to the wheel gear. So I will draw these lines right here. These are going to be tangent lines, right? Tangent lines, and we call that the what? That's going to be like the chain, right? Or sometimes a belt, mainly a chain. Okay, so ultimately, here's what I need to know. The velocity of the bike, which I'm going to call B, should be the same as the velocity, linear velocity of what? If I can figure out how fast the tire, a point on the tire is moving around its circumference, that should be the velocity of the bike, right? That's how the rubber hits the road. If you could figure out like this, if there was a rock in the tire right here, if you could figure out how fast that rock was spinning in miles per hour around the circumference of the tire, that's going to be essentially how fast the bike is moving down the road. That would be the tangential velocity, okay? So if I can figure out the velocity of the tire, I've got my answer. Now, to figure out the velocity of the tire, I need to figure out the angular velocity of the tire, okay? Well, the angular velocity of the tire should be the same as the angular velocity of what? Not the bike itself. What am I calling it? What letter? They're on the same axis, right? Or same axle. Should be the wheel sprocket, right? Because that's kind of like the merry-go-round effect. If this is a merry-go-round and that's an aerial view, any point on that merry-go-round is spinning at the same angular velocity. They're all making one rotation for the same unit of time, regardless of where they are. But if they're farther away, they're experiencing a much different ride because they're moving faster. So the angular velocity of the tire and the angular velocity of the wheel sprocket are the same. They're on the same axle. Okay, so now I need to relate the angular or the wheel to the pedal. And they're connected by the chain. So the wheel sprocket and the pedal sprocket have the same what velocity? Are they spinning at the same rate? They're not spinning at the same rate because then you don't have mechanical advantage. Okay? The back one is spinning faster because it has a smaller radius. Okay? That's how you can transfer your power. But they are connected by the chain. So if you imagine a little bug that's on the chain, he's moving around that system at a constant speed, right? So as he moves around this one and moves around this one, he's moving around them at the same speed. That means they have the same what velocity? Not angular, linear, right? So the linear velocity of the wheel is the same as the linear velocity of the pedal. Next time you're pedaling a bicycle, okay, tie a little string to the chain and just pedal and watch it go around. And regardless of where it's at, it's moving at the same speed, okay, whether it's on the pedal sprocket or on the back sprocket, okay? So they have the same linear velocity. All right, so now I have a formula. I have a way to get from pedaling to the ground. I'm going to go from my pedal to my wheel sprocket and from the wheel sprocket to the tire and then from the tire to the ground. Here we go. Let's go ahead and color code it. I'll use green. Let's go ahead and call the pedal sprocket, okay? What I'm calling the pedal sprocket. The linear velocity is our omega. Well, what is the radius of the pedal? It's 4.5 inches. What is the angular velocity of the pedal? It's 35. I have to start with the pedal because that's what I was given. 35 revolutions per 1 minute. Okay, so notice I have inches revolutions per minute. Inches per minute is good for speed. It's not miles per hour, but it's still a velocity. But revolutions is not. So let's do one calculation here, and let's get rid of revolutions. One revolution is, again, 2 pi radians. So revolutions divide out, and that's going to give me inches per minute. So because this is an intermediate calculation, I'm fine with inches per minute for now. Ultimately, at the end, we'll convert it to miles per hour. So let's go to the calculator and just type in. I'm going to leave the pi out because I don't want to get ugly decimals introduced, and I don't want to have to store values. So let's just go 4.5 times 35 times the 2 from the 2 pi, and I get 315. So that's going to be 315 pi is still there, and then inches per minute. Now, that is not only the linear velocity of the pedal, but that then is the linear velocity of the chain, which means it's equal to the linear velocity of the wheel sprocket. They share the same linear velocity. All right, so let's I'm color coding it again. Now let's move to the back wheel sprocket. So we'll call that the wheel sprocket, what I'm calling W. Again, V equals R omega. V equals R omega. Let's plug in what we know. We know the velocity of the wheel sprocket is 315 pi inches per minute. That's going to equal the radius of the wheel sprocket, which we do know is 1.5 inches, times the angular velocity, which we don't know. We don't know how fast it's spinning. We know it's spinning faster than the pedal sprocket, but how much faster, we don't know yet. So now we'll just solve for omega. We'll divide both sides by 1.5. So we get 315 pi inches. You could do it like this. You could put the minutes down there, inches per minute, and then you can multiply by 1.5 inches right here. And notice what's going to happen with the inches. They'll divide out, and that means radians magically appears. So now we have angular velocity in radians per minute, which is fine. It's not revolutions per minute, but it's still angular velocity. So that ends up being the angular velocity omega of the wheel, so W, which is now equal to the angular velocity of the tire because they're on the exact same axis or axle, okay? They are both spinning at the same rate. Okay, so now I can make the transition to the tire. So let's start a new column here. Oops. We'll call this the tire. And again, the linear velocity is equal to r omega. We're trying to figure out the linear velocity, v. So we plug in the radius of the tire, which was 14.5 inches, times the angular velocity, which we just found to be 315. We didn't get an answer for that. Sorry, I didn't go to the calculator. My bad. Let's type that in on the previous one and see what it is. I'm going to leave the pi visible, but I'm going to divide it by 1.5. Okay, now because it's still my calculator is 315, I'll just divide it by the radius, and I get 210. I forgot to do that. So that's actually 210. Pi is still there, and that's going to be radians per minute. So that's a better number to use than 315 pi divided by 1.5. So that's what we use over here then. The linear or the angular velocity of the tire is the same as the wheel that we just found, 210 pi radians per minute. And that means then, let's go ahead and multiply that one. And again, I'll leave the pi visible. Now we're taking the 210 and we're multiplying it by the other radius, 14.5. And we get 3045 pi. 3045, 3045 pi. And that's going to be units of inches per minute. Now that is not only the velocity of the tire, linear velocity of the tire, that is the linear velocity of the bike. Okay? That is the linear velocity of the bike. The only problem is inches per minute is not now the final units that we want. We want it in miles per hour. So let's go ahead and do one last thing here. 3045 pi, we'll have inches divided by 1 minute. And then we'll just do some stoichiometric conversions to get it to miles per hour. And then we'll come back and summarize what we did. Okay? So let's do the time first. I've got minutes up here, and I want hours down here. So 60 over 1, and that gives me hours. And now I need to get from inches to miles, but I have to go through feet. So there's the conversion right there, 1 foot in 12 inches. That gets your inches to divide out. And now we'll do 1 mile is 5280. And again, you have to know that, 5280 feet. And that gets your feet to divide out. And before you pick up the calculator, you just analyze your units, miles per hour. Okay, so that's good. So now, because we want our final answer, the velocity of the bike moving down the road, now I'll go ahead and multiply it all out, including the pi. All right, I'll come back to that here. Let's get an answer. It should be reasonable. I could just take my answer. So I could just hit second negative or just go times pi. We'll multiply it in there now. Times pi times 60 divided by 12 and then divided by 5280. And we should get a reasonable number. Looks good. 9.058 or 9 miles per hour. So essentially what we're saying now, to summarize, is on this bike, which would be like one of those new mountain bike size, if someone is pedaling around 35 miles per hour, which is just a little bit faster than once every 2 seconds, kind of a meandering pedal, right? It's traveling at 9 miles per hour down the road. Very reasonable. Now, I want you to see, because it looks like it's very complicated, it's really just one equation. What we're doing is we're really just establishing what's called gear ratios. All right? If you're into mountain biking or you're into like working with cars, especially transmission, gear ratios are really nice. That's why we have different gears. We can use mechanical advantage to help us, either get more torque or to get more speed. We're starting with 35 RPMs. Essentially, here's what we did. We took the number we started with, minus the conversions. We simply took that, we multiplied it by 4.5. See that? Then we turned around and divided it by the next radius, 1.5. And then we turned that around and multiplied it by 14.5. So essentially, we multiplied. Let me multiply by the first radius, which was 4.5. Then we divided by the next radius of 1.5. And then we multiplied it by the next radius of 9.5. So that would be like a 4.5 to 1.5 to 9.5 ratio. And you could figure it out. Let's go ahead and see what that would be. I'm just kind of curious. Notice you can see right here, times 4.5 divided by multiplied. You can see the work right there. Everything else is just a conversion. So 4.5 divided by 1.5, and then times 9.5. This will kind of tell you your mechanical advantage, and then we just hit math enter to convert it back, and you have a 57-2 advantage, okay? So that's what that means. In this bike, in this particular gear, there's a 57-2 advantage, which is good. So for every 57 units, or for every 2 you expend, you're multiplying that by a factor of 57, okay? That's pretty good mechanical advantage. All right, so those are gear ratios. Everything else is just a conversion. We took the number we started with, we divided by, or we multiplied by 4.5 first. That gave us the linear velocity. Then we divided by 4.5. That gave us the angular velocity. And then we multiplied that number by 14.5, and that got us back to linear velocity. If you wanted to leave it as revolutions the whole time, you don't have to do this 2 pi radians over 1 in the beginning. You could do all of your conversions on the back end if you wanted. Okay? In other words, you could have done this. You could have said, okay, 35, I'm going to multiply by the first radius, 4.5. I'm going to divide by the second radius, 1.5. I'm going to multiply again. I guess I should keep that the same. I'm going to multiply by the last radius, 9.5. And then I'm going to convert. Okay, that's essentially what we did. So I'm not going to give you a problem like this tomorrow in the quiz, because I want you to do that thing called homework and practice a little bit more. But this definitely will be on the test. Okay? So make sure you know how to do that. Your quiz question will be more like the warm-up from today or the last one from Friday, okay? Which is like example 8 or like the warm-up. All right, so that's it. We're done with this section. Make sure that when you go outside, you appreciate now the wind and realize what it's from, okay? All right. I pledge allegiance to the flag of the United States of America, to the republic for which it